This is a lecture given as part of an atmospheric electricity course at South Dakota School of Mines and Technology. It was given on March 26, 2013. It's entitled Lightning Flash Types and Components Observed with High-Speed Cameras and Correlated Electric Field Sensors. As far as an overview, we'll be looking at the leader theory, leader behavior differences based on high-speed observations correlated with electric field sensors. Then we'll look at flash types and flash components. We have two vehicles that are modified for optical observations. Here's one of the vehicles. It's a van that has a panel that can open up, as well as some glass bubbles for cameras with wide field of views. From inside the van, you can see we have the cameras pointed out the side of the van. And here's a high-speed camera, another high-speed camera, a digital still camera that's infrared triggered or takes sequential images at night. A high-definition camera that records at 1280 by 720 at 60 images per second. And then we also have a couple other wide-field standard definition cameras, and there's also a bubble on the roof of the van that has a all-sky view standard speed recording. The second vehicle that we have is a modified truck, and the front right passenger area has been modified to house an array of cameras as well. It has two high-speed cameras here and here, and a high-definition camera, and here I'm taking pictures with a digital still camera that's infrared triggered. As far as the instrumentation that we use, we have been collaborating with IMPE Brazil and Dr. Marcelo Sava, and his equipment involves fast and slow antenna, flat plate antennas. And here's one of our locations where we have three flat plate antennas. These are two fast antenna with a very short time constant in the millisecond range, and these have two different gains that allow us to record received signals with a higher dynamic range. The high gain antenna amplifies the received signal so that we're able to resolve the lower amplitude signals that are received, and the low gain antenna does not have the amplification and therefore tends to not saturate with the higher amplitude received signals. So between those we're able to get a higher dynamic range of received signals. We also have a slow antenna, which is also a flat plate antenna, but it has a longer time constant in the tens to hundreds of milliseconds, even over a second as far as the time constant goes for the slow antenna. And this allows us to see the entire flash before the time constant causes a recovery back to zero after the signal stops. We also have a couple of electric field meters. Here's a Boltec electric field meter at the same site as the flat plate antennas. And this is a slow antenna from New Mexico Tech. We also have a site in the middle of Rapid City that contains a single fast antenna. This is a low gain fast antenna, and it also is co-located with a Boltec electric field meter. And the electric field meters again provide the ambient electric field. They record at 50 samples per second. The IMPE sensors record at 5 million samples per second. Since 2007, when we first started using the high-speed cameras, we've captured 76 flashes, so over a total of 6 years. 206 of those were positive CG flashes, 2 of which attached to towers, and 372 were negative CG flashes, 3 of which attached to towers. We've also captured cloud flashes in which visible leaders were visible outside of the actual clouds or below cloud base 158 different times. And we've captured a total of 41 upward flashes with the high-speed cameras over that same time frame. Electric field data was added in 2009 and has been operating since. To begin with, we'd like to talk a little bit about monopole lightning theory. In the original thinking as far as how lightning develops was that these charge regions form in clouds, and these charge regions then launch a leader of the same polarity as the charge source, and this leader then would propagate to the ground or to another charge region, and upon contact with the ground would cause a return stroke that would essentially neutralize or discharge that entire leader as well as part of the cloud charge source. Now, the same idea it was thought that a monopole leader would be launched from a charge region and propagate towards another charge region of opposite polarity, and upon reaching that charge region would cause a discharge, kind of like touching your finger to a doorknob. And again, this would cause a discharge that would neutralize or discharge the charge buildup in the two regions of opposite polarity, and you're left with less charge overall after the flash. And this was thought to be the case for many years. And in 1960, Heinz Casimir proposed that instead of a monopole leader, that rather their lightning is composed of a bipolar, bidirectional leader with zero net charge on the leader. And this idea in theory was challenged for many years and challenged rather strongly. And it wasn't until the mid 1980s that this idea was actually shown to be viable. During the 1980s, there was a F-106 aircraft that was flown through thunderstorms specifically for the purpose of being struck by lightning. This was piloted by the gentleman on the right here, and the gentleman on the left was the engineer or research scientist that sat in the back seat. And this aircraft was struck numerous times. It had sensors, current measuring sensors, as well as optical recording equipment, standard speed recording equipment. And what Dr. Vlad Mazur was able to do was use radar to show the bidirectional development of the leaders as they initiated from the aircraft, since the aircraft was in fact the one causing the strikes. And since lightning itself, the ionized channel leader channels can reflect radar energy, he was able to see this bidirectional from the tip and the tail simultaneously propagate away from the aircraft, and the current measurements supported this as well. And we can actually see that there's a number of aircraft initiated strikes on YouTube now. This particular one that I'm going to show you is from Australia, and this was an aircraft coming into Sydney, Australia, and a gentleman was filming his kids playing soccer and happened to pan up to an aircraft on its approach right when it got struck by lightning. But the thing we want to notice here, before I play it, is here's your aircraft, and you have a leader that initiated from the nose of the aircraft and went upward, and you can see the branching is away from the aircraft, or away from the flash origin. And also from the tail area, we see a leader that went downward. Again, we can see branching away from the aircraft, indicating that this in fact was a bipolar, bidirectional development. So we'll take a look at that. So the initiation of the flash from the aircraft did cause a multiple cloud to ground lightning flash. You can see the pause in between the different strokes, and you can see a little bit of the plasma that's trailing behind, likely melted off metal from the lightning strike as well. So in this particular case, aircraft initiated strike causes a multiple cloud to ground flash as a result. So now our current thinking as far as how lightning develops is that essentially you have a region of positive charge indicated by a positive Q here, and I'll use red coloring to indicate positive charge. and negative Q, or negative charge. And this creates an electric field between these two charge regions. And the electric field points away from the positive charge in the direction in which a positive test charge would move under the influence of this field. And the sign convention, the atmospheric electricity sign convention, is such that a downward pointing electric field is considered to be positive. I suspect that this came about the fair weather electric field, since the atmosphere is slightly positively charged in the fair weather condition. This is called the fair weather field, and the electric field is pointing downward, but that was considered a positive field, and so um, the sign convention follows the potential gradient. Now, the physics sign convention, a downward pointing electric field is considered negative, using the positive z-axis from the Earth pointing upward, and therefore it's the negative of the potential gradient. So it's important when you look at electric field data presented by any electric field sensor to understand which sign convention is being used. And in most papers, the authors will state that early on so that it's clear throughout the paper. Otherwise, you have to kind of figure it out yourself. Um, so in this case, we have a downward pointing electric field due to the charge arrangement. And we still don't know exactly what causes the leader to initiate. The institute measurements of electric field values are such that spontaneous initiation of a leader is not likely to occur due to the thresholds not being met inside the storm. So there's a number of theories out there as to why the leader gets started. This could be cosmic radiation causing initial ionization, leading to electron avalanche or runaway breakdown. Also, it's thought that it could be possibly the hydrometeor's shape, which enhances the electric field locally, could cause the breakdown value to be reached, or an arrangement of hydrometeors. So it's still one of the big remaining questions relating to lightning is how the leader actually gets started. But when it does start, it develops in a bidirectional bipolar fashion, as you see here. And if we look at it in detail, we can see that on the positive end of the leader, electrons are liberated, or ionization takes place in the corona streamer zone out ahead of the leader, and this causes the electrons to move inward towards increasing electric field, and then they travel towards the negative end of the leader. On the negative side, we have an outward pointing electric or field, basically we have an inward pointing electric field, and the electrons are moved outward under this electric field. And so you're left with a surplus of electrons in the negative end and a deficit of electrons in the positive end. So then you have a positively charged end and a negatively charged end of the leader as it develops. So the electron flow then is towards the negative end, and again, depending on your sign convention of the current that you're using, physics would be in this direction, um, then we can see how the leader develops as a result of this ionization that's taking place. Now, there's very few actual observations of the bipolar breakdown in naturally occurring lightning. We've only captured this a couple times, actually about 4 or 5 times, and it always seems to happen when we do capture it. It seems to happen near positive leaders that have propagated horizontally below cloud base. This is what you're looking at here. This is captured at 100,000 images a second at a positive leader that propagated upward and transitioned to horizontal propagation. The tip of the leader is outside the field of view, and then near the leader we saw this leader develop. There was no previous activity in this region at all, and what we'll see is a leader develop bidirectionally. The positive end will move away from the positive leader. It'll be more continuous in nature. The negative end will branch right away and clearly step much different than what we see the behavior of the positive leader. And the negative end will then connect with the positive leader, causing a bright connection. And what you also want to watch during as a result of the connection is notice the luminosity front will travel down the positive leader, and once reaching the tower causes an even brighter luminosity front to return back up. And then what follows is that a new branch has been added to this upward leader. So the newly formed branch then continued for the rest of the flash duration. We can also see some of the features associated at the tip of the leader. Here we have a positive leader or positive end of a leader that's developing. We can actually see the corona streamer zone, and notice how the fan shape of the corona streamer zone changes shape and direction as the leader propagates. It almost appears to kind of split where it attempts to branch or undergoes a sharp direction change. So we'll take a look at positive leaders. This is a flash captured at 100,000 images a second, recorded a positive CG return stroke by the NLDN, estimated to be 23.3 kiloamps peak current. And we'll notice in this particular case that the leader does not branch, it remains bright and luminous, and it does seem to have some periodic pulsing along the entire length that originated near the tip and traveled back along the leader. There is one attempted branch coming up here, there. It's unsuccessful, and then it continues. You can see the corona streamer zone, and there's the return stroke. Now, if we look at negative leaders, we'll notice quite a difference. Again, we'll see clear stepping, much more branching in this particular case, and that the tips are quite bright where the stepping is taking place. This also was recorded at 100,000 images a second. These are actually branches from a main channel that's just outside the field of view to the right, and then it will make a connection with ground, causing a return stroke, and the NLDN indicated it was a peak current of estimated peak current of 30.3 kiloamps. And you'll notice when the return stroke does take place that the branches are or do participate in the return stroke. And are essentially no longer active after the return stroke. Well, as we started filming the flashes with the high-speed cameras, we immediately started noticing clear differences between the positive and negative leaders. And I've kind of highlighted the differences that we have seen here, and we'll talk about each of these as we go along. The stepping behavior of positive leaders tends to be much more continuous compared to negative leaders. We do see some periodic pulsing, but it's clearly not as distinct as the stepping that we see with the negative leader. As far as the brightness of the tip of the leader, if the positive leaders are not branched or widely branched, just a few branches, they can be quite bright. However, if they do branch prolifically, the branches tend to become very dim, very difficult to see. The negative leaders, on the other hand, the tip brightness remains very bright no matter how much branching takes place, And as we saw previously, the stepping tip is very clearly visible and quite bright. As far as the directional change, the positive leaders tend to meander almost with no sense of urgency uh, compared to that of the negative leaders. The directional change is quite erratic, and this may be associated with the stepping nature. It's unclear, but much more erratic compared to the positive leaders. And then as far as the localized branching, these are branches that remain close to the main channel. Um, Again, if the positive leader has a lot of localized branching taking place, these branches tend to be very dim and sometimes very hard for the high-speed cameras to pick up. Whereas the negative leaders, the localized branching remains quite bright and visible to the cameras. The last time I'm going to discuss as far as the differences between the two is the branch redevelopment. And we'll focus on this because the implications that we're seeing relating to this branch redevelopment uh, plays a significant role in the different components of the flashes. And so to start off with, if we look at the positive leaders, we see that if we do have a branch, and here we have an upward propagating positive leader, we have a branch that branched off to the right, and what we see as far as these branches that decay is that they decay from the branch point outward, and that even with the tip still visible and no visibility or luminosity visible further back, we then see the development of a bidirectional, bipolar leader that's aft of the tip of the leader that has become cut off from the main channel. And so this leader then develops in a bidirectional manner, and a lot of times the positive end, upon reaching the extent of the positive leader tip, branch tip, will cause some forking to take place, and the negative end then travels back towards the main channel. When it does that and it connects to a luminous channel, causes a bright luminosity front to return back up the branch, re-illuminating the entire branch. And if the luminosity remains, then it's essentially reconnected or reionized that decayed branch. Now, in the case where a main channel is weakly luminous and this branch decays, we can see a number of different things happen with the negative end of the recoil leader. The negative end could come back to the branch point and actually go up further away from the flash origin. And when that happens, most of the time they decay shortly after going up. We can also see them split, and so we see a portion of it go up and go down. Or we see the negative end of the leader extend past the branch point and continue towards the flash origin. Now on the negative leader, when we see the branch decay, we don't see it decay in the same manner. We see the branch pretty much decay uniformly along its entire length, and we don't see a tip that's still visible when redevelopment takes place. For the purposes of this discussion, I'm going to call this a prograde leader, and I'll explain that as we go through the different points here. But essentially what we see is that the leader redevelops or reionizes from the branch point outward instead of a point aft of the tip of the decayed branch. And so this redevelopment then causes luminosity to increase outward from the branch point. And when that happens, we also tend to see some brightening in the main channel back towards the flash origin. Now again, if the main channel is weakly luminous and this branch decays, when we see this redevelopment take place, we'll frequently see luminosity also propagate away from the branch point towards the flash origin. And this would indicate to us this a bidirectional nature, likely bipolar, as far as its redevelopment goes. So in this particular case, in the negative leader case, it's primarily and the prograde direction along the decayed branch, whereas the recoil leader on the positive leader branch is dominantly in the retrograde direction. Now, the frequency at which this redevelopment in the negative leader branches is quite rare compared to how often we see the recoil leaders form on positive leaders. We see that quite often with positive leaders, but quite infrequently with negative leaders. We don't seem to see any kind of triggering mechanism or an induced process that causes the recoil leader to develop, and that is also true for the negative leader. However, there are times when luminosity fronts will travel up the the leader path, and upon approaching a decayed branch point will cause the redevelopment of a decayed branch. So this redevelopment on the negative leader side can be induced. So real quick before we move on, as far as the naming goes, if you look in the literature, this redevelopment along positive leader branch has been studied for quite some time, and essentially what the electric field signature that's created as a result of this redevelopment is a K change. And so this redevelopment has been referred to in the literature as recoil streamer, recoil leader, K streamer, K event, K leader, K process wave, K wave, negative retrograde leader, and dart leader. I'm going to use the word recoil leader here. Ogawa and Brook in 1964, they have a paper that they define the recoil streamer as being a recoil or return stroke type event when the positive leader made contact with negative charge region. So they hypothesize that that's what caused this fast negative leader to propagate back in the opposite direction. So they use the word recoil to be the same as return. Mazur, 2002, stated that since this is a leader process, that leader would be more appropriate to use instead of streamer. So he preferred to use the word recoil leader, and that's the word I'm going to describe here. Now, if you look back in the literature, I was not able to find anything that describes the redevelopment on negative branches. And so again, I'm defining here in this talk this negative branch redevelopment as a prograde leader. Now, it's a nice two-syllable word, similar to recoil. Is it the best word to use as far as this redevelopment? Well, that remains to be seen. I will say that there are words that are common to both a negative and positive branch redevelopment, and I've listed some of those below here. They both act to reionize a decayed branch, whether it be positive or negative, but they tend to do it in a different way. So they're both really reionization leaders. Other words that I've heard brought up are reconnection leaders or rebreakdown leaders or redevelopment leaders. So this is the naming convention that I will use in the rest of this talk. So let's look at recoil leaders that form on decayed positive leader branches. This is an upward positive leader from a tower, and it's filmed at 1,000 images per second. And we're going to focus on the branch indicated by the yellow arrows as well as that indicated by the white arrows. We'll focus first on the yellow arrows. And you can see we have the branch point here and the tip of the leader branch extending, and we start to see the luminosity decay from the branch point outward, and with the tip still visible, we see the first recoil leader, and then we'll see another one still with the tip barely visible. Now if we look at the white highlighted, again it's starting to decay. We see the tip is still visible. There's the first recoil leader, and there'll be another strong one that illuminates the trunk from the branch point downward. So this shows us that, sure enough, we have positive leader branches that decay, the luminosity decays, but we're still able to see the positive leader tip before the recoil leader actually forms. In order to see the actual bidirectional bipolar development, though, we need to have a faster camera. So this is the development of a recoil leader filmed at 54,000 images per second, and it'll play twice here. The initiation point is right here, and we can't see the visible tip because of the short exposure time, but we will see that the bright development of the recoil leader itself. So it'll play a second time here. So we see the initiation, positive end to the right, negative end to the left. And notice that when it connects at the branch point, the luminosity in the trunk below that point brightens up, and we do not see any brightening in the upper portion of the leader branches. So now let's look at negative branch redevelopment, and we'll look at an example of negative leaders, and we have a branch point and a branch that will decay and fade, and then a little while later it will redevelop, but notice that it's from the branch point outward. And also notice that as it propagates outward to the point at which the leader initially decayed, it then renews its stepping as it causes new breakdown in virgin air once again. Let's look at another case. Again, what we had here is a negative leader that came down. There was two branches that branched off. The leader propagated, and then these branches decayed. And notice that the luminosity in the main channel is fairly weak when this redevelopment occurs, and therefore also look at how the luminosity also increases back towards the flash origin when the prograde leaders develop. Briefly, before we talk about flash types, we'll hit a little bit on electrification of the storms themselves. Now, earlier in class, you guys had talked about the electrification processes, so we won't get into those. But this just kind of shows that you do have the typical traditional tripole structure of an upper positive region, a main negative charge region, and a lower positive charge region, but that in reality can be a bit more complex, and you can have multiple charge regions, an upper negative charge, you can have screening layers, you can have multiple layers of charge associated with the melting layer and precipitation that's taking place. So for simplicity in describing the different flash types, I'm going to stick with the basic tripole structure. We have the main upper positive charge region, main negative charge region, and the lower positive charge region. And again, we know that this induces opposite charge on the Earth's surface, since the Earth itself is a relatively good conductor and essentially an unlimited charge source compared to the storm. And we also get screening layers on cloud boundaries due to the induced processes of having these charge regions. So we could get negative charge screening layers near the positive charge regions or on the top of the storm above the upper positive region. We could actually get a positive screening layer on the edge of the updraft here near the negative charge region. So as far as cloud flashes or the different flash types, we'll start with normal cloud flash. And now that we understand that the leaders develop in a bipolar, bidirectional manner, and this has also been confirmed with LMA, the lightning mapping array, which can map lightning in 3 dimensions. The flash actually originates in between the two charge regions at the maximum electric field values, and we get the bidirectional development with negative leaders going up into the positive charge region and the positive end of the leader going into the negative charge region. And unlike what was previously thought, these leaders propagate into and through these charge regions, similar to what we now refer to as potential wells. Essentially, they propagate into and through these regions, and this upper positive charge region acts as a positive potential well, favorable for negative leader propagation or development through that potential well. And the negative charge region acts as a negative potential well, favorable for positive leader development to propagate in and through it. And as long as there's a potential difference between the leader tips and the surrounding ambient electric field, the leaders will continue to propagate. When that potential difference stops or decreases to a certain value, then the leader actually stops propagating and decays. So if there was an impulsive event that takes place during this, what we consider to be a normal cloud flash, the NLDN would detect this as a positive IC event. And what that means is essentially it's the sign convention that the NLDN came up with. And if you have downward propagating positive leaders, and say you have a bright, strong, impulsive recoil leader that makes a connection with an existing channel, that could be registered as a positive IC event by the NLDN associated with a cloud flash. So really between any charge regions we can get this development associated with a cloud flash. So in the case of it, what we call an inverted cloud flash, we would have initiation between the negative charge region overlying a positive charge region, with the positive leaders propagating up into the negative charge region, negative leaders propagating into the positive charge region. Now, if a impulsive event occurs during this, again, here's an example. If we had a recoil leader that initiated and had a bright impulsive connection with the main channel, then it would be likely registered as a negative IC event by the NLDN, again, given the orientation of the leaders. In the case of a ground flash, in this particular case a negative ground flash, we have the development between the initial development between the two charge regions like before, but what is thought is that this lower positive charge region, essentially the negative leaders propagate into this positive potential well, but given that it is typically smaller than the negative charge region, it essentially fills up the potential well and then continues past that positive charge region and continues until connecting with ground. And again, the NLDN would record the return stroke that takes place with this event, and the return stroke essentially then raises the ground potential up into the channel, up towards the top of the leader structure, and essentially you're left with a upward propagating positive leader that is propagating through the negative charge region in the middle portion of the storm. And so the return stroke and the impulsive return stroke that takes place, again, given the orientation of the leaders, negative charge is effectively lowered to ground. This would be a negative CG. So let's look at this in a little more detail. And we'll play this animation one time through. I'll talk and then we'll go back over and take a look at it. So we get the two charge regions. We get the negative leader connecting with ground, causing the return stroke. This may decay, and then we might get the development of a recoil leader along the decayed positive leader branch. The negative end, if it travels down to the ground in the same path, could cause a second return stroke to take place. And while a main channel is luminous, we could get another recoil leader to initiate and connect with a luminous main channel, and this could cause M component brightening. So let's take a look at that individually. Again, we get the bidirectional development between the two charge regions, and it continues to ground. First thing is the return stroke, and the best analogy that I've heard that I could actually visualize is the concept of the return stroke being that you essentially, if you were to take a column of frozen water, and if you were to touch it to a hot plate, what would happen? Well, you'd get a rapid melting of the ice into liquid form, and then that liquid form would accelerate to the ground due to gravity. And you can think of the return stroke as being an acceleration front of electrons that are suddenly touch a conducting surface um, that allows for rapid current flow. And so the electrons that have connected with the ground now see a very significant drop in resistance. And so you get an acceleration of electrons that has a cascading effect or cascading front that propagates back up that channel towards the top of the leader network. So essentially it's a cascading front of accelerating electrons in the downward direction. And so this return stroke that propagates back up the channel propagates all the way to the top of the leader network, and you're left with a essentially a growing upward propagating positive leader following the return stroke. Now this can continue to grow, and if it does, the main channel will remain luminous due to the growth of the leader, and that is what we call the continuing current that we see in the main channel following the return stroke, is simply the growth of the leader following the return stroke. Now if it does in fact fade, then what we've shown is that recoil leaders can form on decayed branches aft of where the tip of the leader was, and the negative end then can propagate back, and in the case of a decayed main channel can propagate all the way to the ground. This essentially is a dart leader, and if this dart leader reaches ground and causes a return stroke, this would be the second return stroke of a multi-stroke negative cloud to ground flash. It's the same polarity, negative CG in both cases. And this will re-illuminate that channel. And then what we've also seen with high-speed cameras is that we can get recoil leaders formed on decayed branches when the main channel is still luminous due to the propagating leader end. And if those connect with the main channel while it's still luminous, we see brightening along the main channel that has a much shallower luminosity increase front compared to the dart leader return stroke brightening. And this is the M component brightening that we see is very much more slow hump, if you will, as far as the luminosity curve that it portrays. And we can see that with the connection of a recoil leader during that luminosity, ongoing luminosity. So let's look at some examples now with correlated electric field measurements. And this first case is a 3 is negative CG flash with 3 return stroke. It has 1 attempted dart leader that does not make a connection with the ground. And here we're going to be using the physics sign convention, and this is from the fast antenna, low gain. It was fairly close to the flash, only 1.6 kilometers away from the return stroke, and this was captured by both the fast antenna and the slow antenna. And we're going to play the video off to the left here, and you'll see the corresponding electric field signature. Since we are so close to the sensor, or since the flash was so close to the sensor, we see the leader field change as it approaches the sensor or the ground, and then the rapid opposite direction deflection due to the return stroke. And then we see pulsing associated with recoil leaders here, and again the leader change associated with the approach of the dart leader in this case, and this is the attempted dart leader, and then the last dart leader and return stroke here. So let's take a look at that. Kind of speed forward to the dart leader, but then I'll slow it down for the dart leader. So Here comes the dart leader. Second return stroke. Attempted dart leader. So this was also recorded with the slow antenna, and with the slow antenna facing downward, it actually records the data in the atmospheric electricity sign convention. So in order to eliminate the confusion and mental gymnastics to make the conversion between that and the physics sign convention, I've essentially flipped the trace in the vertical, so now it's also in the physics sign convention. You'll see that the numbers are actually upside down, but we'll just concern with the shape of the trace. So that the slow antenna then, with a longer time constant, we do see the same direction leader field change, and then we see the negative change due to the return stroke, and we see it more in a step fashion now. We see the dart leader associated with the second return stroke here, and notice that we do get an ongoing field change in between the two events, or a J change, and that we get a step here associated with the attempted dart leader. Essentially, this is a K change due to recoil leader, that the negative end does not make it all the way to the ground, and a slight field change since it's deviating away from the zero value, that is due to leader development. Likely leader development within the cloud that we don't see below cloud base, simply leaders that are independent leaders that are still propagating. And you can see that the NLDN recorded 3 negative events, the last one being the strongest as far as the estimated peak current. So let's look at another case. In this case, we're going to see the difference due to the distance of the sensors away from the actual return stroke. And so we had a negative CG that was located here. At 1.2 kilometers away was one of the sensors, and then the other sensor that had 2 fast antennas and the slow antenna was located at 7.2 kilometers away. So if we just look at the field trace from the fast antenna low gain that was 1.2 kilometers away, we can see a very similar trace than what we just looked at. We see the leader change, the return stroke, the negative change due to the return stroke, the dart leader, field change, return stroke, again dart leader, return stroke. So very similar to what we just saw without the attempted leader. Now if we move away, same fast antenna low gain now at 7.2 kilometers away, we're actually beyond the reversal distance. And so you guys have discussed the reversal distance. So now when we see the leader change, it's actually deflects downward due to being beyond the reversal distance. We see the leader change and then the negative deviation due to the return stroke. And notice that all the pulses are also in the other direction than the previous plot. And we can see this a little more detailed by using the high gain, which amplifies the signal. Again, we can see the stepping associated with the negative leader, so this gives us this pulsing nature of the leader change, and we see less of it in the dart leader or shorter time period, but we still get some pulsing due to likely what we'll call dart step leader. And we see these recoil leaders or attempted dart leaders as well. If we look again then at the slow antenna, we can see the leader field change in the same direction downward, and now we see the definite difference of using a longer time constant, and we actually see the step changes associated with each of the return strokes and the field change in the interim period after the return strokes, and notice that they're all deflecting downward away from the zero line, or showing a negative change in this case with each of the return strokes, and then we also see the steps associated with the K changes associated with the recoil leaders. Well, one of the things that we've been lucky enough to capture is actually the development of the recoil leader that results, that essentially is the dart leader that causes the subsequent return stroke in the same channel. This, what we're looking at here, is another negative cloud to ground flash, and this is the second return stroke that we're going to look at, and we're going to just focus on that. We actually see a recoil leader develop at this point here, and the negative end continues on down, and here we see it as the dart leader that's about to make another connection with an estimated peak current of negative 7.4 kiloamps. This was recorded with a fast antenna and low gain, about 6.1 kilometers away from the flash. And what we'll see is that here's the field change to the initiation of the recoil leader. This is the sharp negative change due to the return stroke. And what happens is we'll see another recoil leader initiate from a decayed branch here, while this channel is still luminous shortly after the return stroke that takes place from the original first recoil leader. And so we see a positive change due to the initiation of the second recoil leader, and then when it connects with the now luminous channel, we see a negative deviation that's a bit shallower. And then we see a series of additional recoil leaders that initiate, but when they connect with the main channel, the negative change is much more shallower, and these are M components. And we'll see that. We'll watch the main channel and notice how it brightens in a more uniform manner, and the luminosity increase is much less abrupt when compared to the dart leader connections. So let's take a look at that. Recoil leader, negative end emerges from the cloud. Subsequent return stroke. There's the other recoil leader. And now we'll see a series of recoil leaders that brighten the main channel as M components when they connect with the main channel. See much more shallow luminosity rise and corresponding electric field response. If we look in detail of that first recoil leader and connection, we can see that this is associated with the development of the recoil leader, and then here's the abrupt return stroke, negative change due to the return stroke. You can see how sharp that is. And then this is a continued negative change following the return stroke due to the redevelopment of the upward positive leader that's essentially left behind. We get a little sharp response during the development of the recoil leader. It connects with the main channel, and we see the negative deviation due to the M component brightening. Same thing here, we see the recoil leader initiate. There's a little impulse during its formation, M component brightening, and the pattern is repeated. What we also see with negative leaders as they propagate to ground is that sometimes they become independent from the main channel from which they branched and will not participate in the return stroke itself. And this is an example in which there's a main channel return stroke of an estimated peak current of 19.3 kiloamps, and then there's subsequent connections by orphaned or independent branches that formed originally but did not participate in the return stroke. So we'll take a look at that. We can see all the branching taking place originally that dim. We get the first return stroke here, and then that's followed shortly in time by this second one. And after a couple milliseconds, we get this other independent branch make a connection. Notice that the luminosity does not go back up into the cloud and connect with the original branch that came from the cloud. Same thing with this other one as well. So even though we do see some luminosity, some weak luminosity, the return stroke type brightening does not travel up into the main channel network. If we look at that with the electric field instrumentation, this is the fast antenna, low gain, about 11 kilometers away from the NLDN indicated stroke. We can see the negative field change associated with the first return stroke, and this is the second one that was none of the three that followed were recorded by the NLDN, but we do see negative, sharp negative deviations in the field corresponding with their connection, but a much smaller amplitude. So here's the third, and then here's the fourth. Let's look at another case. This particular case, the first one showed as a negative 11.6 kiloamp estimated peak current. So there's a negative leader propagating downward. We see a branch. When the first connection is made, that branch does not participate. And then we get an independent connection. In this case, it does travel up into the leader network. And what's interesting about this flash is after the return stroke, typically we're left with then an upward propagating positive leader in the upper portion of the flash. Well, notice how these leaders, the return stroke channels decay quite quickly following the return stroke. And then this branch then continues as a negative leader, clearly has characteristics of a negative leader. So essentially, we have the upper portion of the flash, the positive end, and the negative end. So now it's behaving like a cloud flash, even though the return stroke has already taken place. So it's transitioned back into the bipolar leader network. Again, if we look the data recorded by the fast antenna, again, this is a low gain. This is about 7 kilometers away. We see the connection made by the first leader channel here, and then here's the second independent branch when it made its connection. And this did not register anything with the NLDN. So now let's look at positive ground flashes. And again, we get the bipolar bidirectional initiation in between the two charge regions. In this case, we get the negative leaders propagating up, negative end of the leader propagating up into the positive charge region, positive end. And in this particular case, propagating towards the negative screening layer at the cloud boundary, and it continues past that and on to ground, forming a positive CG return stroke. And in this particular case, the ground potential then is raised up the channel, and we're left with a upward propagating negative leader following the return stroke that's propagating into the positive charge region. Again, we'll look at this in detail, and we get the positive leader coming to ground this time, get the return stroke that propagates up the channel. And again, at this point, if it continues to propagate, we would see the luminosity remain in the main channel as the leaders propagate, and this would result in a continuing current. And with positive cloud ground flashes, we see this quite often with long continuing currents as this dendritic negative leader development, this new breakdown, if you will, that initiates at the end of the leader network that formed prior to the return stroke. This causes new breakdown in virgin air, and we see that in many cases with the positive ground flashes, a long continuing current due to this negative leader growth. Well, if this were to decay, then theoretically then we could get the similar scenario where in this case a prograde leader from the branch point outward could develop, and so you have the prograde direction negative leader and then the positive end developing downward, and this could then be the dart leader that comes back to ground, causing another positive CG in the same channel. This is actually just a working theory as to how this could happen, because we have not had the opportunity to see that type of development outside of the cloud, we have captured 4 different positive cloud to ground flashes in which we recorded a second positive CG return stroke in the same channel that had correlated uh, electric field information that showed that they were in fact both positive CGs in the same channel and correlated NLDN data. So there are a few times in which you can get a positive CG flash in which you get a multiple stroke in the same channel, but it's quite rare. Typically, any multiple flash or multiple return strokes that we see with positive CGs tend to be in different channels associated with branches that make new termination points to ground. So that's a working hypothesis as to how that may come about. We have yet to visually see it due to the fact that most of the time this upper portion of the leader network is obscured by clouds. What can happen then, though, if this is after the first return stroke or a subsequent return stroke, if you do have the growing negative leader following the return stroke, you could have a decayed branch, and again you can get a prograde leader that develops from a branch point and propagates outward along that decayed branch to reionize that decayed branch. And this, then we could see some M component type brightening along that main channel characteristic with M components. Again, we have not visually seen this prograde development due to the upper portion being obscured. But again, this is a working theory as to one way to cause M component brightening with a positive CG flash. I think the other ways that we can get the M component brightening in either positive or negative CG case is simply the propagation of the leader into the areas of varying potential that cause the induced luminosity increase and induced current flow along that conductive leader due to the result of the encountering potential differences as it propagates. So that's a positive cloud to ground flash. And let's take a look at a couple of these. Now this is one example in which we actually see that both the positive and the negative end of the leader. We see a positive end, basically a non-branch meandering bright positive leader propagate to ground, causing a return stroke, which recorded an estimated peak current of 19.1 kiloamps by the NLDN. And we can actually see the upper portion, at least a branch of the upper negative leader development associated with this bipolar development. And what we'll notice is after the return stroke takes place, we'll see an enhancement, very rapid brightening in the negative leader development, and essentially you're left with an upward growing negative leader following the return stroke. So let's take a look at that. There's a positive leader, negative leaders, get the return stroke, and notice the rapid brightening and acceleration of the negative leader development in the upper portion of the flash. Well, here's another example of a positive leader that has a meandering nature. This was what we showed at 100,000 images a second. We're now looking at 10,000 images per second, and we're going to contrast this with the next flash. But again, this is an example of how a non-branch positive leader behaves. And what we see quite often in the northern high plains is what we're about to show you, and that is the positive leader that propagates to ground tends to be highly branched, very weakly luminous, and produce numerous recoil leaders as it propagates to ground. Once it gets closer to the ground, the main leader or main branches will brighten and accelerate and no longer produce recoil leaders and then make the connection with ground. And this is a very common occurrence with the positive cloud to ground flashes that we see in the upper high plains in the United States. And talking with our colleagues in Brazil, kind of the opposite is the case, in that they typically see the bright, non-branching, meandering positive leader, and then rarely see this behavior with the branching and the recoil leader production. So on the right, this is going to be an integration, a time integrated example of this flash. So once the recoil leaders show up, they'll still be present on the right. Can barely see the recoil or the main leaders as they're propagating. And then as it approaches the ground, it brightens and accelerates just prior to the return stroke. So this is a very common pattern with positive cloud to ground flashes. And we also see the positive leader independence that we showed earlier with the negative leaders, in which a leader branch will become cut off from the main channel and propagate independently to ground and can connect with the ground after the first return stroke by the main channel. We're going to see this example here with a positive cloud to ground flash, and the first one records an estimated peak current of 25.6 kiloamps. And then this branch makes a connection later. And notice that the luminosity does go up, but dominantly does not go all the way back up into the main channel. And this was recorded at a estimated peak current of 13.4 kiloamps. And there's just been 2 papers published, or the second one's in the process of being published, headed by Stolzenberg and Tom Marshall from Mississippi, Ole Miss, and they have described these, what they have defined them as UIs, or upward illuminations, as being mini return strokes that take place due to independent or orphan branches that continue to propagate and do not participate in the original return stroke of the main channel, but then subsequently make a connection to ground independently and have this illumination that rises up but does not travel back up into the main channel branches themselves. The papers that they published were only associated with negative cloud to ground flashes, and but this does show that it also occurs with positive cloud to ground flashes. So let's talk about a few other types of flashes, and essentially Harold Edens from New Mexico Tech recently completed his dissertation, and they looked at bolts from the blue, and what they found was using LMA data and high-speed imagery and photography and such, that essentially bolts from the blues are cloud flashes in which the upper portion of the flash, the negative leaders that propagate into the positive charge region, essentially the leader propagates out of the charge region, exits the storm updraft, and then travels quite some distance from the updraft and connects with ground. And a majority, if not all of these, I haven't read all of the dissertation yet, were associated with negative cloud to ground flashes, so that there's a negative leader that exits the cloud and propagates to ground. Now earlier I showed that you can get these positive cloud to ground flashes in the vault region due to the upper positive charge region and the bipolar development in between the screening layer. And so we do see a lot of positive cloud to ground flashes in the vault region or under the anvil section of the storm, but these bolt from the blues that initiate out the side of the updrafts are typically negative. And here's an example of one by Mike O'Neill in Australia. And you can see the main updraft. Here's the inflow band into the updraft, and this is probably at least 5 or so miles, up to 10 kilometers away from the storm itself. The other scenario that you can get is actually initiation between the upper positive charge region and the negative screening layer on the top portion of the storm. And again, if this propagates past that negative potential well, it can continue upward into the above the thunderstorm. And this is defined as a blue jet. And if it were if anything impulsive was recorded by the NLDN, this would show up as a negative IC. Alternatively, if we had a lot of mixing due to convective turbulence and such, and that negative screening layer essentially was mixed out and so it was not present, you could get a similar case of the bolt from the blue, except the negative leader doesn't go out the side but continues upward and goes up above the thunderstorm. And in this case, it's the negative leader, and that's defined as a gigantic jet. And again, if there was an impulsive event during that particular scenario, it would be recorded as a positive IC by the NLDN. And so we now have an idea of actually how the blue jets and gigantic jets arise, or a theoretical idea based on LMA data and correlated optical imagery. And so the blue jet is in fact attached to the storm itself as well as the gigantic jet, and initiates and is part of a flash that initiates in the storm. And this is different from transit luminous events such as sprites or elves, which are independent of the thunderstorm. They are triggered by parent flashes, typically positive CG flashes with lots of charge moment lowered to ground or high charge moment change. And these then cause a disturbance in the electric field, a large change in the electric field that is present between the thunderstorm and the ionosphere, and therefore we get bidirectional breakdown in the upper atmosphere in the form of a sprite, or we get the ELV events or halos that are present due to a triggering flash below. So if we look at a paper that was published by Kreibel et al. In 2008 in Nature Geoscience, they essentially showed all these possibilities that I just described in this paper, as far as with the basic tripole structure and the positive blue jet, the negative bolt from the blue, negative gigantic jet. And the thing that we found during STEPS, which is a severe thunderstorm electrification and precipitation study in 2000, there was a very large campaign based out of Goodland, Kansas, and what was found from that, from data collected from that study, was that storms can occasionally take on an inverted charge structure. So essentially, an upper negative, a main positive, and a lower negative charge region, opposite of what we typically see. And sometimes storms can even change their polarity during the storm itself. They might charge initially as normal polarity, and then later have an inverted polarity charge structure. So all of these possible combinations are based on the normal tripole structure. But if this is inverted, you can essentially have the same types of flashes, just inverted polarity from what we just described. But that's not all. So there's more we need to talk about, and we'll get into those next. And this is what I call secondary events. And these are events that take place after the initial development takes place with the flash itself. And so if you have the case where you have a cloud flash, in this case an inverted charge structure where you have a negative over positive, and you have the negative leaders propagating downward, positive leaders propagating upward, you can get that flash decay, get a recoil leader, and then in this case the negative end comes down the leader structure and re-energizes the development of the lower structure as well as the upper positive leader development, and still remains an inverted cloud flash. Alternatively, this negative end of the recoil leader could come down and actually take a new non-previously used path to ground and form a new termination point. So essentially it travels down and transitions to a negative cloud to ground flash after an initial cloud flash takes place. By the same token, and again this would be less likely or less frequently because again we don't observe this prograde development as often as we see the recoil leader development. You could get a prograde leader develop at a branch point, and then it could develop, and the positive end could travel all the way up into the upper portion of the flash and cause renewed development in the upper portion and essentially reinvigorate this cloud flash. Or again, it could also take a new path to ground and cause a positive cloud to ground flash. Well, if we have the normal charge structure, basically we could have all these combinations again just in reverse. If we have an upper positive, lower negative charge region, we have a cloud flash that occurs between them and then decaying take place. Now we have the decayed positive leaders closer to ground, and the more likely scenarios are the initiation of recoil leaders. And so if we get an initiation of recoil leader, we could see the negative end could travel up into the upper portion and initiate new development and essentially re-energize the cloud flash, or alternatively it could come to ground and take a path to ground where the negative end comes to ground, forming a cloud to ground flash. And we actually have seen this a number of times, and this is actually not that uncommon to see positive leader development, and then during some of the recoil leader that form, occasionally some of these will then, the negative end will then transition to ground and form a negative CG stroke. And so we'll actually look at an example of this, and we had positive leader development that is propagating up here. There's been no development seen below this cloud base other than the positive leader development with multiple recoil leaders taking place. And what we'll see is the recoil leader forms, the negative end propagates to ground, forming a estimated peak current 33.6 kiloamp negative CG return stroke. So there's a recoil leader, the negative end is highlighted. And then we see new negative breakdown downward to ground. And the return stroke, notice the upper portion, now the positive leaders are growing following the return stroke, but it quickly decays and the recoil leader activity continues in earnest. Now another possible scenario is a bipolar ground flash in which we have a positive CG followed by a negative CG in the same channel. And we've actually captured a number of these, 6 total between the operations in Brazil and in South Dakota. And our theory behind the formation of a negative CG in a previously used positive CG channel is as follows. Is essentially we think we have a positive charge region and a lower negative charge region, and we think this negative charge region is most likely associated with a screening layer right at cloud base. So the cloud base extends down to this point right here, and so we have this negative charge region right at cloud base. And we see the bipolar development, we see the positive leader come down, but during that process, one of the branches that actually is propagating horizontally through this negative potential well actually becomes cut off from the main channel and therefore does not participate in the return stroke and acts as an independent positive leader, which we've shown to be possible. in that it later then develops a recoil leader whose negative end propagates back towards the main channel. But now that the main channel has decayed, is no longer luminous, but still somewhat conductive, that it reaches this channel, and actually the negative end now, instead of going up into the upper negative leader network, which is now decayed, actually goes down and travels down that conductive path, causing a negative CG return stroke. So we'll take a look at that idea. Get the bipolar development, positive leaders coming down, decaying branch that is cut off from the return stroke channel fades, the positive leader continues independently, forms a recoil leader, the negative end travels back to that main channel and propagates to ground, causing a negative CG return stroke in the same channel. And we've seen this happen, and then following this initial negative CG, we've seen multiple negative CGs continue to occur along that same path as this channel fades following the return strokes, and a new recoil leader initiates retracing this path over and over. And we'll take a look at that. Here is a example with high-speed video of 10,000 images a second, and we'll see that the NLDN recorded first a positive 38.9 kiloamp return stroke. And there's the positive leaders with recoil leaders propagating downward. See the first return stroke, and we did see a branch that was active via recoil leader activity initially, and there it is continuing to be active following the return stroke. The main channel is decayed, and then we see one of the recoil leaders, the negative end, propagates back towards the main channel, follows the channel to ground, causing a negative cloud to ground stroke. And another. And this just keeps continuing. So if we look at the electric field data associated with this, flash was recorded by the fast antenna. Now we're using the high gain, because since we're 24 kilometers away from the NLDN indicated location of the flash. And what the NLDN indicated were there were two positive events. We actually saw those on a high-speed camera. There was a short independent positive branch that connected, forming a different termination point nearby. But the first one was a 38.9. Interestingly, the NLDN indicated that was a cloud flash or cloud event. Clearly it was connected to ground. Same thing with the other independent leader that connected to ground. So we see the positive deviation in the electric field due to the positive cloud to ground flashes, or return strokes rather. And then we see the negative events associated with the subsequent negative CG return strokes. And it went into the next second. This one did not get recorded by the NLDN. And so we have an example of positive cloud to ground flash that has negative CGs that follow the positive CG return stroke. The question is it possible to get a negative CG flash that has positive CG return strokes in the same channel following the first negative CG return stroke? And to date, we have not recorded any events of this nature. So I'm just going to present two possible scenarios that might lead to this type of event. Again, even though we have not been able to find anything in the literature associated with naturally occurring downward flashes. And so The first scenario is that we essentially have a negative cloud to ground flash, negative leaders propagate downward, cause a return stroke, so we're left with an upward positive leader. This leader decays, and as we've shown numerous times, that we can get a recoil leader on decayed branch. And in this particular case, we're hypothesizing that the negative end of the recoil leader could come to the branch point, and like we showed, sometimes they propagate outward instead of continuing back towards the flash origin. Well, if this were to happen, and we do see that quite often, typically they fade shortly after this occurs. So if this recoil leader then fades, there could be a scenario which we're at a branch point, we could get a prograde leader develop, and then we have negative leader development back out that branch associated with the positive end of the prograde leader propagating down this channel. And if it extends all the way to the ground, this would be a positive CG return stroke. So let's take a look at that scenario. Again, negative CG return stroke, the leader network fades, get a recoil leader that then fades, and then at the branch point, a bipolar prograde leader whose positive end extends to ground, causing a positive CG return stroke. So that's a hypothesis. Another possible scenario, and we actually saw evidence of this associated with an upward positive leader that developed from a tower in Brazil. And essentially what happened here is we had an upward positive leader that developed from a tower. It branched with the left branch going in this direction and the right branch going up in this direction. Now this leader network decayed, and this branch remained very active in producing recoil leaders. And so we had the negative end of the recoil leader coming down, and if it made connection with the tower, cause bright return strokes. And since the negative end would be the end coming to ground and causing the return stroke, we would see this as negative CG return strokes. And so we essentially have a negative charge being effectively lowered to ground. Well, this entire leader network decayed, and then a recoil leader formed. And during this process of the decay of the upward positive leader, a brand new bipolar leader development occurred over in this area. And the negative leader, the negative end went into the cloud, and the positive end was clearly visible due to its behavior and propagation. Uh, and this positive leader was present out to this point, and this recoil leader developed. The negative end went down to the branch point, turned upward, like we've shown can be the case with recoil leaders, and actually continued outward towards this positive leader, the positive end of this leader development that developed, and actually connects with the positive end of this leader development. And what happens is when this connection is made, there's a rapid extension of this positive leader downward along the negative leader path of the recoil leader, and instead of extending all the way out to extend this positive leader branch out to this point, it continues downward through this somewhat conductive path, although it's not luminous, and it reaches the tower as a positive leader, positive end of the leader, and causes a bright, very strong positive CG return stroke. And then we're left with this entire leader network that extends into the cloud now, and this is a positive cloud to ground return stroke, and that's what the lightning location system detected associated with this particular event. And then this flash continued for some period of time following this. So let's take a look at that. There's the recoil leader, the negative end turns the corner. Here's the positive leader end, extends up towards it. We see brightening in the positive end and a bright return stroke the curves that follows. So that's another possibility, is essentially if you get new leader development associated with a particular flash, the negative end of a recoil leader could essentially connect with that new development and cause a positive CG in a previous negative CG channel. So now we'll talk about horizontally extensive flashes, and these flashes are typically present during the decaying portions of storms, usually when storms mature into kind of a cluster, multicellular clusters that have fairly large areas of coverage. A lot of times we'll start seeing these very horizontally extensive flashes associated with the decay of these types of systems. We also see them with mature mesoscale convective systems in which we have a leading convective line or convective area followed by a trailing stratiform precipitation area. And these types of flashes can travel tens to 100 kilometers in distance, and multiple cloud-to-ground strokes can be present with them. And so we'll talk a little bit about what we're seeing with the high-speed cameras as well as the correlated data that shows up. Back in the 1998, Mazur et al. Published a paper where they observed some what they referred to as spider flashes, and these were horizontally extensive flashes that they observed during the decaying portion of a thunderstorm complex in Florida. And they had an all-sky high-speed camera capable of filming at 1,000 images per second, as well as correlated to interferometer data and electric field data. And based on their observations, they saw a number of flashes in a fairly short time frame, and some of these were cloud flashes. One of them was also a positive cloud-to-ground flash, and they saw this horizontal extensive leader development that took place associated with these flashes. And what we'll show here is actually the video from one of the cloud flashes that they analyzed. And their findings based on their data was that these horizontally extensive leaders that were visible were negative leaders, and they were part of intercloud flashes and positive cloud-to-ground flashes. And their electric field data supported this in that the ambient electric field was essentially was negative, and that when they saw the leader development, they saw a positive change in the electric field due to the leader development, which was attributed to the negative leader development. So we'll take a look at the example here, and it's a little hard to tell. Unfortunately, a lot of it was pretty saturated, but we see the bright luminosity, and then we start to see some leaders visible below cloud base, and you can see them here. You can kind of see some detached leader segments up in this region, and then a main channel here and here. And now that we've had a chance to view lots of high-speed recordings with the cameras that we're using now, this does in fact to me look like negative leader development. So I do agree with their findings. I think that in this particular case, that the visible leaders below cloud base were in fact negative leaders, and we have seen that here in the northern high plains on occasion, but not as often. In fact, quite often we see positive leaders, and we'll get into that in just a second. But here's an example of some horizontally extensive leader development, and these were in fact negative leaders. And here's an example of a positive cloud to ground flash in which negative leaders were propagating just below cloud base following the return stroke. So on occasion we do see similar observations as what they found in Florida. However, um, about I would say 80 to 90% of the time when we see horizontally extensive flashes here in the northern high plains or anywhere in the plains for that matter, um, we actually see what appears to be positive leaders below cloud base. We still see in-cloud brightening that propagates above cloud base, and this tends to precede the positive leaders that we see. And on occasion, we can see that in-cloud brightening to be caused by negative leader development. So we think that it's still driven by negative leader development, but in the plains anyway, a lot of these are associated with negative leader development above the cloud deck or the cloud base, and that we see positive leaders that tend to trail behind below cloud base. And what we think is going on in these cases is, again, a similar scenario that we presented earlier, is that we have a cloud-based extension down to this point. We have in the case of what we see in the plains with the positive leaders below cloud base, we think there's a positive, horizontally extensive positive charge region that's favorable for negative leader development. And then we also develop either a negative screening layer right at cloud base, or maybe negatively charged precipitation that's falling below cloud, which acts as a negative potential well favorable for positive leader development. And if we look at some of the literature that's been written about the horizontally extensive flashes, MCS type systems, I think Carey et al. 2005 had a paper that correlated with LMA data and showed that a lot of these horizontally extensive flashes were associated with positive cloud to ground flashes that initiated in the convective region, and then the negative leader development traveled in a sloping positive charge layer that sloped backward or back towards the stratiform precipitation area, and that so that the LMA showed this to be the case. So we think there is a horizontally extensive positive charge region, and that what happens is you get the bipolar development in the case of a cloud flash, and you do get the negative leader development that travels quite a long distance, but uh, what you see visibly below cloud base is actually positive leader development. And this tends to trail behind the negative leaders that travel out ahead of it. And here's an example of this. This is a very wide angle view of a horizontally extensive flash, or spider or anvil crawler, as some people refer to them. And what you'll see is negative leader development, kind of the pulsing that we see associated with negative leaders that kind of precedes the positive leaders that are trailing behind. And so we see the negative leaders first visually above cloud base, and then these are clearly positive leaders propagating horizontally below cloud base. And you can see that they branch widely initially, and then as they decay start to produce numerous recoil leaders. And this, by the way, is a very wide field of view, probably a total of 50 kilometers at least in the horizontal as far as the field of view goes. Well, we can see this sometimes. This is was going to show a portion of a horizontally extensive flash or a spider flash, just a portion of it, and we will see that these are in fact positive leaders that are producing, that are cutting off and then producing recoil leaders. Integration going on the right side and real time on the left. And sure enough, these are in fact positive leaders that have become cut off and then produce recoil leaders. Sometimes the negative end then deviates off the main path, as we see right here, and I'll do it again here shortly. So this is actually the negative end deviates off the original path taken by the positive leaders. And this was a very small portion of this flash. The flash was filled up pretty much the whole sky as we viewed it, and this is just a small segment of it. If we look at the electric field signature of this flash, um, this just highlighted here in the black of what we just looked at. Um, what we notice is in the fast antenna high gain is that it shows a negative deviation, and this would be indicative of the approach of positive leaders, which is in essence what we are seeing. And all these fast negative deviations are due to recoil leaders that develop on decayed positive leader branches. Now what's interesting is you look at that, you see um, this negative deviation that tends to go back to zero as far as the fast antenna goes, and then we see these numerous recoil leader associated perturbations. Well, what's interesting then is they start to take on a bipolar nature later in the flash. And what's interesting is when we look at the high-speed video and correlate it relative to where the sensor was, these later portions, these later recoil leaders actually formed behind or beyond. In other words, the positive leaders traveled over the sensor and were beyond the sensor, and the recoil leaders formed beyond them, and the negative end of the recoil leader then traveled towards the sensor, which would actually be likely be the reason for these positive deviation as a negative end of the recoil leader approached the sensor and then passed over the leader and traveled away from it, causing the negative deviation. And it was very interesting in looking at the video of how the progression of the flash spatially uh, propagated closer to the sensor, and then we saw these later events, all of which were associated with a portion of the flash that was beyond the sensor and traveled literally right over the sensor, and also noticed the larger amplitudes of the signal given the closer proximity, whereas these were quite a distance away from the sensor um, in a different direction from the sensor, about 90 degrees off from where the other portion of the leader network traveled. Let's look at another case. Again, we're going to see kind of a development of the positive leaders and recoil leaders. This pretty much went right over the head of the camera. And we'll see a quick integration of that. And again, if we look at the field trace from the fast antenna high gain, in this particular case, we actually see a positive deviation first, and then a transition to an even more pronounced negative deviation. And although this wasn't shown on the video, preceding this leader development that you saw, we did see again kind of a pulsing in-cloud brightness associated with negative leaders that preceded the positive leaders, and it was during that time that we see the positive deviation in the field, and then as the positive leaders approached, we saw the negative deviation, which is what we would expect, and all the associated recoil leader associated pulses due to the cutoff or decayed positive branches. So what we're seeing is positive leaders below cloud base, but we also see some multiple flash events following positive CG ground flashes. And in this particular case, what we think is going on is we get the positive CG return stroke, and we get the negative leader development that follows the return stroke, but that leader development decays, and then you can see some subsequent positive leader development following that is separate from the original positive CG return stroke. And in some cases, if these leader branches decay and then become cut off, we can get recoil leaders that initiate back along these positive leader paths, and a number of other things can happen as far as in the same type of flash. But this one that I'm going to show now was captured in standard speed video, but I think it's an outstanding example of just these spectacular spider flashes. And this was filmed in Australia, and this high definition standard speed, I believe it's 30 images per second, and it is filmed with what we call a rolling shutter, which actually causes this linear artifacting. But we're still able to see the features that I want to show you. I want to let it play through once, and then we'll talk about the specific features of what's going on. It's just a spectacular flash. So what we think is going on here is, let me get back here, is we get a positive CG return stroke that causes this initial saturating brightness. And this bright saturating luminosity that travels overhead is actually above cloud base. We don't see any leaders associated with it below cloud base, and that is presumably the negative leader development that follows the positive CG return stroke. And there actually is a channel that's visible, the return stroke channel that's visible right here, associated with a likely positive CG return stroke. So we get a positive CG with return stroke, extensive negative leader development, and then we start seeing the positive leader development that trails behind. And what happens next is that we get the development of this positive leader, and what we believe happens is that we get a recoil leader from that. The negative part of that goes to ground, forming a negative CG return stroke that's spatially separated from the positive CG return stroke. So this isn't a bipolar flash, it's a separate termination. And careful examination of this channel, it shows that it is spatially separated from the first return stroke. And so we get a negative CG and then a second stroke along that same channel, so multiple negative CG return strokes in the same channel associated with recoil leaders that are propagating below cloud base and trail of the negative leader development. And then we get another recoil leader, but this time it goes up into the positive charge region and it causes extensive negative leader development again, which enhances the positive leader development, and we get this huge blossoming of positive leader development that follows. So we'll watch the end of that again. So a very complex situation associated with these horizontally extensive flashes. And just to show here that we can also get negative breakdown that propagates below cloud base associated with one of these recoil leaders. This is just a small portion of a spider flash, and again positive leaders propagated overhead in this direction. They subsequently decayed, and we saw numerous recoil leaders, the negative ends of which were traveling back in this direction, and this one actually initiates new negative leader development that does not go to ground. So we'll just look at that. There's the recoil leaders, and there's the negative leader development. That's now in virgin air as new step leader breakdown. If we look at the electric field associated with that, here's the field chain associated with the recoil leader. There's kind of a pause, and then we start seeing the stepped, more noisy signature of the negative leader development. It's not dominant compared to the recoil leaders that are initiating and propagating, but we do see the signature associated, or the increased noise from the stepping of the negative leader. Another possible scenario with these horizontally extensive flashes is, again, it starts with a positive CG flash. Negative leaders propagate horizontally. The flash decays and becomes cut off, and again we get the positive leaders developing on the cutoff ends of the negative leader. And in this case, instead of propagating horizontally, one of them goes to ground and causes another positive CG return stroke. And so we get basically a multiple positive CG return stroke event separated spatially and temporally. So we get the return stroke negative leader development that becomes cut off, renewed positive leader development on the negative ends, one of which connects with ground, causing another positive CG return stroke at some distance away from the first. And this happens quite often, and this is one mechanism that caused the horizontally extensive flashes to drive such large distances. Here we have a LMA depiction of a horizontally extensive flash, and essentially what it's going to show is you have negative leader. This is altitude versus time, and we'll look at this panel first. And it's also rainbow colored according to time, with blue transitioning to red with time. And so what the LMA does is it looks at in a particular window, and we'll just say it for this purposes, we'll use 100 microsecond window, and it has an array of VHF sensors at different locations that use GPS timing, and each of them looks in 100 microsecond windows and looks for the peak received radio event within that 100 microsecond window, and it uses a frequency band of about 60 to 66 megahertz, kind of channel 3 on the local TV stations. And so it receives radiation in that frequency band, and in that 100 microsecond window will timestamp the highest peak value, or the event and time of the highest peak value in that time window. And all these sites at the various locations will correlate this same peak value with different receipt times, and then use a time of arrival technique to derive the three-dimensional position of that event in that particular 100 microsecond window. And they could use as little as 10 microseconds for higher resolution. So each of these points here is a particular radiated source that was identified in 3 dimensions during an individual window. And so what this shows is that the radiation source is initiated in this region and dominantly went downward, and this is typically associated with negative leader development, which is much more noisy than positive leader development. And then at some point there was a positive cloud to ground flash, and I'll explain how that came about since we initially had negative leader development going downward. The other depictions here are a plane view, which you're above the flash looking downward, and this is north, east, west. And if I were standing to the south looking north, then I would see this depiction, which is basically a west to east oriented 2 dimensions, and then altitude. And if I was standing at the west looking to the east, this is my north-south line, and altitude in this direction of the flash from that angle. These X's indicate the location of positive cloud to ground return strokes, as indicated by the NLDN. So this particular flash initiates in this area, and we'll play this animation here shortly. This flash initiates in this region indicated by the blue, and there's first a positive CG return stroke, more development, and these are negative leaders since the LMA preferentially detects negative breakdown. And this negative leader development continues, and then we see another positive cloud to ground return stroke and trail the tips of the negative leader development. It continues on, and we see another positive CG and even another positive CG, and we can see that this flash travels close to, this is 20 kilometers, 40 from the center of the array. So the first one is about 25 kilometers from the center, and the flash terminates at about, looks like it's close to 50 kilometers west of the center of the array. So this is a very horizontally extensive flash, and so it's traveled well over 40 kilometers, 50 kilometers or so. And so what my interpretation of this, and we'll play the animation, is that we have initial breakdown taking place in this area, and essentially it's a cloud flash to start with, negative leaders down, positive up, and then I think we get new positive leader development on the decayed negative leaders that form the first positive CG return stroke. So following that return stroke, we get enhanced negative leader development after the return stroke propagates along the negative leaders that form prior to the return stroke. And this keeps continuing. And then we get another return stroke here, and it again furthers the negative leader development, and another one, and you can kind of see some blossoming after the return stroke, and then even the last one. And so what we believe is going on is exactly what the animation shows, is you get your first return stroke, negative leader development, these negative leaders become cut off, positive leaders develop on the negative ends. One of the positive leaders go to ground, causing another positive CG return stroke, which then results in more negative leader development, and this continues on. And we've actually been able to capture that with high-speed cameras. And this is a flash here that we're going to show two positive CG return strokes. And what you'll see is the first one is about 28 kilometers away, 54.7 estimated peak current. And you're going to see negative leader development stay just above cloud base and propagate towards the camera. We do see some visible evidence of the leaders in the later stages, and sure enough, they are behaving and appear like negative leaders, as we suspect. And these negative leaders actually result in upward positive leaders from these towers. But notice how this leader network decays, and then we start seeing recoil leaders associated with positive leaders that are developing. We actually see some of the positive leaders now developing, one of which makes a connection to ground, causing another positive CG return stroke. So this mechanism of spatially and temporally separated positive CG return strokes with horizontally extensive negative leader development is very viable and has been confirmed by this high-speed camera imagery. If we look at the correlated electric field data associated with this particular flash, it was recorded with a fast antenna low gain, and this was the first return stroke was again 54.7 kiloamps, and that was 32.6 kilometers from the sensor. We see the sharp positive response from the return stroke, but then we see this huge positive deviation due to the negative leader development as it propagates towards the sensor, towards the towers, and towards the camera. The upward positive leaders initiate in this region and continue to about this point. So it's unclear to me if this reversal in polarity of the field change is actually due to the positive leader development from the towers, because they were rather weak leaders. So I'm not sure if that caused the reversal or if it was just the properties of the original cloud to ground flash negative leader development that caused the reversal. But we get the reversal, and then we start picking up visually the positive leader development that's developing to ground and the associated recoil leaders, which are reflected in these small deviations. And then eventually, one of the positive leaders makes another contact to ground. Again, we see a positive, sharp positive deviation with the return stroke. Interestingly, the NLDN again classified the second return stroke as a cloud flash or cloud event, when in fact it was a cloud to ground return stroke. But then following that return stroke, we then transition back to a positive deviation due to the negative leader development that follows that return stroke. And notice that this was much weaker than the first one, with similar deviations due to the return stroke, but that's because of the different distances. You had a much stronger event further away, a much weaker event closer, so they had about the same amplitude in deviation as far as the positive change reflected by the fast antenna. So the last item I'm going to talk about here is attachment. And this is a very important aspect of lightning, obviously, for lightning protection and how it attaches to objects on the ground. And essentially what happens is we get the negative leader, that in this particular case, a negative leader coming downward towards a tower, and due to the enhancement in the electric field by the tower, we get this very visible, very bright upward connecting positive leader that initiates from the tower tip and rises up and connects with the downward propagating negative leader. So we'll take a look at that and see the negative leaders come into view. We already see the positive leader starting to initiate from the tower. It rises up and connects. So there's our return stroke. And decay of the return stroke channel after connection. Interestingly, you can see a slight dimming in the leader channel at this point, likely at the exact connection point between the two leaders. This flash produced dart leaders, about 5 more dart leader return stroke sequences following this first one. And after, when the dart leader came down and caused a subsequent return stroke, there was no dimming present at this location. So this was clearly not an artifact. It was a real feature. This is an example of a digital still image taken by a storm chaser in Kansas, and I believe it was in Kansas, and he was very close to the flash, in the order of 100 meters or so. And what he was able to capture was actually these upward connecting leaders that did not connect with the downward leaders, but these are about a meter tall. This tallest one's about a meter tall. I did an analysis of this imagery and measured all the distance, and this tallest one was about a meter. And what we see is upward leaders initiating from blades of grass, and you'll notice that there's some downward branching at this leader and then upward branching with these 3 connected leaders. So this all kind of rose up, but it actually attached fairly close to ground within a couple of meters or so. And so we can still get a upward connecting leaders even from flat surfaces if there's any kind of irregularities such as grass or such. But the upward connecting leaders can be rather small in length. And as far as attachment goes, here we did get the opportunity of capturing a positive cloud to ground flash attached to one of the towers here, and this actually triggered an upward flash or an upward leader from a nearby tower. And what's interesting about this is that we had a sensor that was fairly close. The fast antenna low gain was 1.2 kilometers away. It was a fairly strong return stroke, estimated peak current of 124 kiloamps. And there's been a lot of debate as to whether positive leaders step, and in the literature there's been a number of reports of stepping that in the last few milliseconds of a positive cloud to ground flash, and that's been attributed to the positive leader itself. Well, what this shows is that actually we had an upward connecting negative leader that initiates from the tower, and as we'll see as we play this video, is that the stepping that occurs in the fast antenna signal is associated with the initiation and development of the upward negative leader, not the positive leader. So in this particular case, the positive leader was relatively silent compared to the stepping associated with the negative leader when it developed and made the connection. So let's take a look at that. There's the positive leader, and we'll slow it down. There's the initiation of the negative leader and the stepping signal starting to be received. And the connection. So this was a great case to show that the stepping that's seen in the last couple milliseconds likely could be due to upward connecting negative leaders that develop from objects. So in summary, as far as the different components of flashes, we believe that continuing current is simply the current in the channel due to leader growth. It was believed, and in fact you'll see in the literature, continuing current is defined as a quasi-stationary arc between cloud charge and the ground. And based on our observations, we don't really feel that there's anything stationary about it. It's simply the current that results from a leader as it continues to grow. The leader doesn't reach cloud charge and essentially plug into it like a battery and cause a continual arc between that cloud source. It actually propagates into the charge region, into the potential well, and continues to propagate until there's the potential leader difference decays to the point that the leader stops propagating and the leader itself decays. A K event or K change is a recoil leader that develops on a cutoff positive leader branch. And as we showed with the video and the corresponding electric field data, this recoil leader development on the decayed positive leader tends to be bidirectional, bipolar, and it initiates in trail of the tip of the decayed positive leader branch, which is very different from what we see with negative leaders that tend to redevelop from the branch point outward in a prograde direction. Dart leader is simply a recoil or prograde leader that reaches the ground. And we've now been able to see that quite often with the high-speed camera and correlated electric field sensors. We believe an M component, or some has defined it as an M event, is the luminosity rise and fall in the main channel connected to ground due to a recoil leader connection, or possibly a prograde leader development, or a brand new leader that forms nearby. As we showed in the video, we can get the new leaders that form near positive leader channels and make a connection to that channel, forming a new branch. If the main channel to which it connects is bright and luminous, then it would cause a slower luminosity front associated with that connection, and therefore an M component luminosity change. We also believe that the induced luminosity variations associated with M components could be associated with a conducting channel as it propagates through areas of varying potential, or sometimes recoil leaders and such will form but decay prior to reaching the main luminous channel. And when they do that, that could induce a current change within the channel due to the induced electric field from the approaching but non-connecting leader. And since the luminous leader is conductive, this induced change can cause a slowly varying luminosity variation characteristic of an M component. And finally, a J change, which is the electric field change that is seen in between return strokes of ground flashes. The literature talks about charge being repositioned or moved around following the return stroke in preparation for the next return stroke. Again, we believe that it's simply independent branches or leader growth that's not visible below cloud base that's ongoing in between the return strokes that cause this field change. So it's simply the ongoing leader growth of other portions of the flash. So I'd like to conclude with a quote by Dr. Vladislav Mazur, who I got the chance to work with for a number of years. From the first time I started working with him, he said to me in a very strong Russian accent, lightning is beautifully simple. There are only leaders. And essentially his philosophy was that leaders form, they propagate, and they die and decay. Um, you can have other leaders form nearby and make connections. You can have recoil leaders form on decayed branches, but it's all a matter of just leaders that form, propagate, and decay. Occasionally you can get a portion of the leader network that forms that touches the ground, and when it does, essentially it's coming in contact with the ultimate doorknob in the sense that the Earth is a outstanding conductor and essentially an unlimited charge source relative to the storm, and that can cause a return stroke to take place. Um, Essentially, that cascading arc of accelerating electrons that propagates up the leader channel. But once the return stroke reaches the extent of the leader network that formed prior to the return stroke, it essentially continues as a growing leader following that from that point on. So his idea was that it's not as complex and hard to describe as you would believe it to be based on the literature, and that it's really a simple process. And keeping that perspective in mind, I think that that is consistent with what we have seen with the high-speed cameras and the electric field data. And I would agree with this philosophy based on what we're seeing. So with that, I will conclude. Thank you.